Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to look at a different problem, which is regarding decision trees and parity checking, and also we'll learn how to reduce the height of decision trees. We've got a lot to cover, so let's start by reading the question first. Draw the full decision tree for the even parity functions of 4 Boolean variables a, b, c and d. Is it possible to simplify the tree? Okay, so first, to start from the very basic, we'll briefly see what is a decision tree and proceed likewise. So the first thing, we will understand what is a decision tree. A decision tree in basic terms is like a flowchart model for classification and regression. So classification is for classifying different objects into different labels, and regression is simply pattern identification from a given data set. So first we'll see internal nodes which are there inside the tree will behave as test attributes, right? For example, is A equal 1, is B equal 1, likewise. Then we have branches. So branches are possible answers that can lead from this particular decision junction. Okay. The third is leaves, which give predicted output, right? And they are the final class label or value that has come from a chain of decisions, right? Or test attributes being of some specific value. Okay, then we have some characteristics. One, it is simple to interpret. Each root to leaf path is a rule. Okay, so this is something that we'll keep in mind. Then other properties are: one, tests are usually on single input attributes. Trees can be binary, yes or no, or multi-way, right? So the test that we do, right, what we saw in the internal nodes above, are made on single input attributes, right? Now that was for the node. Then we see that trees can be binary, which is yes or no, or multi-way. Okay, meaning that a single node can either lead to just two values, or it can happen that a single node leads to more than two values, right? So this can be simply yes and no, and this can be many values as per the problem. Then we come to depth, which is the number of tests on the longest path. We just saw that each root to leaf is basically a path, that is signifying a rule. Okay, depth are the number of tests that are present on the longest of such paths. Then there is decision tree that can represent any Boolean function, but required size or depth depends on the function. Okay, so what this statement says is any Boolean function which we see in expressions can be written as a decision tree, but the size of that decision tree, the size meaning the depth, okay, the depth of that decision tree will depend on the function that we are basically decoding. Now we come to parity, right? What is parity, and specifically even parity as per the question. So parity of a set of bits is whether the number of ones is even or odd, right? It's very simple. We just check the number of ones in that particular set of bits. Even parity outputs 1 if the number of ones is even. Simple, as per the name suggests. If the number of ones is even parity is true. If the number of ones in the bits is odd, then the output would be 0 for even parity. For odd parity, this would be reversed. Now for 4 bits a, b, c and d, the function f of a, b, c, d equal 1 if and only if a plus b plus c plus d is equivalent to 0 mod 2. In Boolean algebra, odd parity equals a XOR b XOR c XOR d. So even parity is simply the whole inside a negation, a XOR b XOR c XOR d inside the negation mark. Then we have the application area. Where is this parity used? So the first one, usage, is obviously in error detection and correction, right? So if the function we can make which can help us detect if the answer is true, then okay, the test is passed. If not, then the test is false, right? So that can be processed into a parity checker and the result can be obtained much faster. Then we have cryptography, which also specifically in learning parity with noise is a standard hard problem in cryptography. Then there is complexity theory and learning theory. So this is a very important part in this particular paradigm. Then there is feature interactions in ML. Parity is non-linearly separable and needs all variables to be in place. Okay, so that was kind of the applications here. Then we find to the actual solution to the procedure. Then we come to the actual solution procedure to the problem. So a standard decision tree that tests attributes one by one, say in order A, B, then C, then D, will have depth 4 and 16 leaves, right? Makes sense, because only A once checked will then move to B and then C and then D, right? So this sequential way of processing leads to a depth of 4. Then we see that each route to leaf path corresponds to one complete assignment, right? Just as we saw, it corresponds to one complete rule of A, B, C and D. At the leaf we output 1 if the assignment has an even number of ones, else 0, right? When we get even number of ones, we mark even parity as 1. Okay, now we come to the rule for leaves. Given a path with specific values A, B, C, D, which is 0 or 1, leaf output is 1 if A plus B plus C plus D is even, that is 0, 2, 4. Otherwise, leaf output equals 0 if A plus B plus C plus D is odd, 1 or 3, right? Another way of representing it, which forms the basis of the compact representation, is truth table. So for that, we just simply put these all together, right? We already know how to arrange A, B, C and D in truth table. We find the number of ones. For here it's 0, here it's 1 and likewise, right? Here it is 2, here it is 2 and so on, right? We simply draw the truth table for this one. If there had been more, here we see 8 zeros, then 8 ones, so there would be 16 zeros, 16 ones, then 8 zeros, 8 ones and so on, right? So at column 3, this is the important one. Here what we do is we count if the number of ones is even, then even parity is 1, right? So 0 is even, so 1, 1, 0, then 2, so 1, then 2, so 1 and likewise, right? So we calculate that. Then we figure out that there are 8 assignments with even parity, output 1, and 8 assignments with odd parity, that is output 0. So if we put this into a decision tree, how would that look? So taking A as 0, there would be other case as well, but let's continue with this one. So if A is 0, then we've got like 2 cases that may arise, either B is 0 or B is 1. If B is 0, then we can have 2 more branches, which are if C is 0 or C is 1 and likewise, right? Once we reach to the bottom, right, likewise as we continue to do this thing, see how we are repeating the branches here, right? So this entire branch got repeated with this one, right? So this happens in the sequential ordering. Other thing that we should note is this particular yellow boxes denotes the even parity bit. So in the first branch pathway, this one, we see number of ones is 0, right? So even parity is 1. Then we see this path, right, starting from the root. So here we see the number of ones is 1, right? So even parity turns 0 and so on, right? Here also we will see there is 1 ones in this particular path, right? So even parity will be 0 and likewise. Then we see that A equal 1, right? This we saw for A equal 0. A equal 1 will have a symmetrical subtree with outputs flipped relative to A equals 0, where the number of ones will increase by 1. So, you can imagine the A equal 1's tree which will be exactly identical to this. Only thing is the number of ones would increase by 1. Why? Because this would be 1, right, and so on. The even parity bits may also get swapped. Now, we come to the next part of the question, which is it possible to simplify the tree, right, which is the important question. So, for that we will first figure out some conditions. So, if only allowed tests are single variable tests, meaning that at a single point in time we can only process one variable, whether it is 0 or 1, then it is single variable test. So, in that case we can't reuse or merge any of the trees, right. So, in this case we can't reduce the number of leaves or the depth of the tree, whatever it is, it needs to be that. Now, we come to the other part, which is how can you simplify when you are allowed to make other changes, right. So, there are actually two, I have mistakenly put it three, two main ways to simplify the representation. First is feature engineering. So, we create a new attribute here, which is p equals a's or b, or p can also be written as a's or b's or c, and then build a smaller tree using these features, right. So, example, we compute x as a's or b and y as c's or d. Then the even parity would be negation of x XOR y. Okay. If computing XOR is allowed as a single test, then the tree depth can shrink, as we just saw, right, because now there would be less leaves, which we will see down below. So, that would occur, right, which if we see, we have made a diagram here. So, the XOR tree circuit would look something like this. We have got A, B, C and D, right. XOR 1, this which is also called x1, is A XOR B, XOR 2 is C XOR D, right, and this one would be x1 XOR x2, right. So, in this way we see that the depth of the tree is 0, 1, 2, right. So, it is 2 here, but in the above case it was linearly dependent on the number of nodes, right. Here it was 5, which is n plus 1, right. So, we got here 5, which is n plus 1, right, and that department which we saw can simply be changed by the number of XORs we do at each step, right, which greatly reduces the depth of the tree as well as the nodes. So, here we see we have got in total about 16 nodes, and also to make things a bit clear, this is a part of the tree, right. There should be also a equal 1 and then the root, right. So, there would be one more level. So, that is how it will be, and so we can see both the depth and number of nodes are much higher than the method we just saw with XOR method. Next, we come to decision DAG or OBDD, ordered binary decision diagram. So, we will see first if merging identical subtrees is possible, which we just saw in the above diagram, that is reuse nodes or produce a DAG instead of a tree, right, directed acyclic graph. Parity admits a compact OBDD of size O of n for fixed variable ordering, right. We will see how this comes with an example. So, we will track the parity so far 0 or 1 as you read the variables, that is A, B, C and D, right. That gives you only 2 states per level, right. So, the whole DAG has O of n nodes, roughly 2n. This particular thing, as we will see in the diagram below, is no longer a tree now, right. It is more of a DAG, which we will see though, and see how it is different from that. It is reduced to an ordered BDD, which is a binary decision diagram, and is a standard technique for compact representation of similar functions like parity. So, for diagram we will see this one. Okay, now we will see the OBDD method. So, in this one what we do is at each step we will have two separate decision nodes which tackle the different scenarios, and that is why we say that we have two end nodes here. This is not a tree though, we'll see in execution this one, and at each step we'll know what is the parity. So at first let's start with here. So we get the first bit as 1, so we'll point the parity as 0. Why? Because it is an odd number of ones, so even parity will be 0. Then we see x0. Whenever we see 0, simply put, parity stays the same, right? So p will remain the 0. We see another 0, it stays the same. Another 0, it stayed the same. Finally the output is 0 only. Okay, then we see down below, x starts with 0, we get parity 1 because even number of ones are there right now. Another 0, still parity 1, another 0, still parity 1, another 0, still parity 1, right? At the end the output is 1. So that's how we proceed. Now let's try to look at the middle ones, right? So let's suppose we started with 1 1, then we got another 1 here at this stage, right? So at this stage we got 1, then let's say we went here, right? So we got another 1, right? So 1 2 3, right? Then we got another 1 here. So in total we have 4 ones, right? So 4 ones leads to parity 1. Why? Because there are even number of ones, hence the output is 1, right? Similarly, for any other method, if we try to approach, right, we'll see that we'll get to the exact same parity bit. That is, if odd number of ones are there, we reach here. If even number of ones are there, we reach here, right? No matter how we proceed. So, and in this way we will get all the different like 16 combinations that are possible using this particular OBDD diagram. So that's how you make it. Now we'll proceed to some of the modifications and other techniques that are there. So first we saw feature construction, right, in the problem itself. Add computed XOR features, which is useful to suspect parity like interactions. Then there is ensemble learning and boosting. So parity is not easy for single shallow trees, and when we apply it to ensembles, which are like sufficiently long trees, they can learn. Then we saw OBDD and BDD packages. It is the same, only like ordering is present in one. They are used to compactly represent the symmetric Boolean functions. Then there is parity and neural networks. So for some neural learners, it is a bit difficult to learn. Why? Because single layer perceptron cannot learn parity. We need deep neural networks or higher degree polynomial kernels that can represent the parity. Then there is learning with noise. Then there is error correcting code, which is the parity checking matrices and syndrome decoding. And lastly, this is a higher advanced level topic, which is quantum algorithms. They are basically used in example like query complexity improvements and other applications. So if you do want to learn more about these modified techniques and future scope about parity checking and decision tree optimization, and we also have more questions on this topic similar to these what we've just discussed, which you can find in the Sigma Solver community. So if you do want to join that, you can simply click the link in the description below. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.